simplify how blockchains actually work. My goal here is to kind of give a very introductory level talk on blockchain, and at the same time, hopefully get pretty low level into the underlying technologies. If you've never worked with blockchain before, that's fine. If you've done some work with like Ethereum or another chain, that's fine as well. This is really aimed at giving people an understanding at how things like cryptographic hashes can be used to build blockchains. My hope is that you'll see that it's really not that complicated of a thing. It's really not magic. There's a few like fundamental building blocks, technologies that have already existed, and they're kind of just put together in this new way. So what is blockchain? The phrase immutable ledger gets thrown around a lot. It's a good description. It just basically means a record of things that can't be changed after the fact. It's important to keep in mind that they don't actually prove anything is true. We all, everyone in this room agrees that something is true by whatever, outside the blockchain method we want, and then we record that thing in the blockchain, and then that way it's saved going forward. So next one, background technologies. I'm going to run through a bunch of technologies here. Things like hashes that you probably may or may not already be familiar with. It's fine if you are, it's fine if you're not. I'm trying to go kind of quickly through these. You don't have to understand them fully, but they're the things that we're going to talk about a lot. Hashes are the main thing, so it's relatively boring. But a hash in its simplest form just takes some piece of data and turns it into a standardized output that represents a signature of that data or fingerprint. An example here is that we have these numbers. We have these numbers like 3875, basic hash that we're going to use here, just summing all the digits. 3 plus 8 plus 7 plus 5 equals 23. And repeat that and sum those digits. 2 plus 3 equals 5. That's our hashing algorithm that we just invented right now. So 3875 is the hash of 5, and this is just a number that represents that first number in some way. Just let you know if that number changes. For example, here we go down 1, 3874. Now hash is to 4. You can see that change, but you can see 3884 also results in 5. This is not a very good hash algorithm. There's only 10 possible outputs. There's an infinite number of inputs, and that's a common theme in any kind of hash, is that you have an infinite number of inputs always, because there's anything you put in there. And there's always a limited range of outputs, and so you have to have the possibility of conflicts, of collisions, they're called. A collision is just literally when two different inputs give the same output. So that's an important point we're going to want to remember. Cryptographic hashes are an important subclass of hashes. They're so popular that generally when people talk about hashes, they are probably just talking about cryptographic hashes. They have 5 very important properties. The first is that they're deterministic. All hashes are deterministic, but just to reiterate, a given input will always produce the same output. So if you give it the same 4-digit number, it's always going to produce that same output. One way, this is what makes cryptographic hashes really cryptographic, is that given an output, you can't figure out what the input was that made that output. This is a very, very important property. So it has some output, and there's no possible way for you to reverse that and go back to what the input was, short of just trying every possible input, and that's what brute force. They're fast. This is just useful for people to be able to verify. If I tell you, hey, this thing here has this hash over here, it's very easy for you to check that because you can run the hash very quickly yourself. Collision resistance, we just talked about collisions. Collisions, again, when you have the same 2 different inputs produce the same output. So for cryptographic hashes, we want this collision resistance, as in, it's very, very difficult, if not impossible, for you, the attacker, to produce 2 different inputs that are going to produce the same output. Or if I give you, here's one input, here's its output, you can't figure out some other input that's going to also create that same output. Then the avalanche effect is kind of a cool chaos theory thing. If you remember Jurassic Park, when he's talking about word droplets falling down his hand and the little hairs on his fingers, talking about chaos theory. It's the same idea here, is that tiny little differences in the input to a system can make big, big changes to the output of the system. And that's an important point for cryptographic hashes that we will see. So SHA-256 is an example of a cryptographic hash. Up top here, we have 4 different inputs. So just the word Barcamp with a capital B, Barcamp in lowercase, all lowercases. Barcamp 2018 in all capitals. So the first 2 strings are very, very similar. There's literally a single bit difference between Barcamp with a capital B and Barcamp in all lowercases. And then, Barcamp all caps with 2018 is a little bit longer. It's a different type of input. And then this is not the string Linux mint. This is an actual ISO. I downloaded 1.8 gigabytes worth of data. I hashed it. And so these 4 inputs produce these 4 outputs. And you can see that there's no correlation here. Even though these 2 inputs are very, very similar, you couldn't tell me which 2 outputs were correlated with which ones. That's the important point I'm going to drive to here. Even though this one is crazy, crazy different, as far different from these 2 as it could possibly be, there's no telling here which is which. For the record, they're in the same order. So top one is that, bottom one is that. But as you can tell, there's no indication of which is which. So concatenate and nonce, I'm just trying to define these terms. Concatenate is when you take a bunch of text strings and you just combine them in some standardized way. So the example here, 1, 2, and 3, you just combine that into one string that says 1, 2, 3. You can put some kind of common separator in between there if you want or not. It kind of just depends on what you're doing. So that's concatenation. I'm going to talk about concatenating things a lot. We're talking about taking 2 strings, putting them right next to each other, and then moving on to the next step. And a nonce is a number only used once. This is a common cryptographic thing. It really just means some arbitrary number you just come up with, and then use it for some purpose one time, and then use it again. It's that simple. So now we're going to talk about encryption a little bit. Symmetric encryption is the kind of normal encryption you would use in day-to-day life. If you had a bunch of files you want to send me secretly, and you just put them in a zip file, and you put a password on there, and you email it to me, that would be symmetric encryption. You have to give me the password somehow, and anyone that had that password could decrypt the file, decrypt the zip file. Same password encrypts it and decrypts it. Normal encryption that you probably think of when you think about encryption. Asymmetric encryption is a more interesting concept in that you generate 2 keys. We'll call them A and B. And this pair of keys, you can encrypt a file with key A, and then only key B can decrypt it. Key A cannot decrypt the same things that key A encrypted. And the reverse is also true. You can take any random file, encrypt it with key B, and then key B cannot decrypt it. Only key A can encrypt it. So you have 2 keys. You can encrypt anything with either key, but then only the other key can decrypt it. That's the important point here. So in practice, these are called public and private keys. The idea is you generate 2 keys. You publish one, that's your public key. Everyone can see it. There's no reason to keep it secret at all. Then you keep one secret, that's your private key. And the uses here are that if you want to send me a secret message, like the thing we just talked about where you zip up a bunch of files and you have to email me, and then you figure out how you're going to get me the password without anyone else seeing it. In this case, I have my public key published on my website. You want to send me some files, so you find my public key, you take your files, you encrypt it with my public key, and then you send me those files. And even though everyone else here can see my public key that you use to encrypt it, they can't decrypt it. It's only my private key can decrypt it, only the other key is up here. So that's the first use. Second use is signing things. I think this is a kind of cool use. Is say I took something and I encrypted it with my private key, and I put it out there. I sent it to someone. Anyone could decrypt that thing because they would use the public key to decrypt it, and so that's not very useful for security because everyone can read it. But it just kind of proves that I am the one that encrypted it with my private key. Only I could have encrypted it with my private key. You can decrypt it with my public key. And just like writing your name in cursive at the bottom of the document is equivalent to signing, we've just agreed upon that as a society. We've just kind of agreed as a digital society that when you encrypt something with your private key, that's the digital equivalent of signing. So putting it all together to build blockchains. So a blockchain is really, in its most fundamental form, just some type of data that we're going to hash up so that we know if any part of it changes, and then we're going to take that first hash that's in that block, put it into the second payload of the data in the second block, and then hash that block, and then if anything in the first block changes, it kind of ripples through this chain. I'll kind of repeat this point in a few different ways so it becomes clear, but at the fundamental level, that's all blockchain is. I could put this entire talk as the contents of a block in a blockchain and store it, and then it wouldn't prove anything I said, which wouldn't prove that the accuracy of that transcript is right, but it would prove a year from now when you go back and look at the block for the Barcamp 2018 blockchain talk, that was what was recorded today. That was what we all agreed upon here today in this room. So, hopefully this is probably the most confusing part, but we have some block A. This is called the Genesis block. It's our first block. So just whatever data we want to start out with, that's our Genesis block. We take the hash of it, and then that's our first hash, first block. Now we move on to our next block. Block B, we start filling up with whatever transactions or whatever data we want to record on our blockchain. We then put hash A into block B as part of like the data payload, and then we just have to hash that up. We concatenate, the data payload B with hash A, and that becomes hashed into hash B. So that's the hash of the second block, and it contains that first hash from block A. So we take hash B, put that into the data payload of block C, concatenate those two things together, hash that, and that becomes hash C. So the key thing here is that if anything in the contents of A changed, that would change hash A, which is inside of block B, which would change hash B, which would change block B, so on and so forth. So if anything in an earlier block ever changes, it kind of changes all these hashes, and they ripple down the line. All of the transactions are, the more certain they become. So you can see how when we start layering blocks on top of each other, it becomes more and more like certain that they haven't changed because there's just so much more history there.
Question?
Yeah.
Why concat over XOR?
I mean, honestly,
It doesn't matter.
for the purpose of this talk, I'm just kind of doing the simplest proof of concept of like how we can make a blockchain. I couldn't tell you if there was a really good reason for one or the other, honestly, but I know concat, I think it's more common at least, as far as I'm aware, so, sorry. So here's the diagram of what I just described, block A, block B, block C. You'll see this Merkle root thing. Don't worry, we'll discuss Merkle roots soon, so you don't worry about not knowing what a Merkle root is. But just for the time being, you can treat the Merkle root as a hash of all the data that's in that block. So if we had a bunch of transactions we want to store, we hash them all up, we just call that the Merkle root for now. There's also a timestamp that's pretty self-evident. Nonce, again, don't worry what that is, it's just the number 0 for the time being. And the previous hash is really the key here that makes this a blockchain. So you can see how if I change some piece of data down in this block, that would change this Merkle root and this thing. This gets hashed up, stored here, which would ripple through this whole process. So here's a problem. Hashes are fast. We talked about that earlier. They're fast on purpose because it makes it easy for people to use them and to verify that what I say is true. But if we go back here, the hashes are fast. If I do change something in here, it's actually pretty easy for me to generate all these blocks after the fact because each hash takes microseconds to generate. So if they're fast, we want a way to slow them down, but we ideally want a way to slow them down, and that doesn't make it slow for people to verify. It only makes it slow for people to generate. That leads us to this thing called hashcash. Has anyone ever heard of hashcash? I'm just curious. It's a really interesting concept that I was very disappointed never caught on from like the 90s. The idea is that it cuts down on spam by making it so that spam is a little bit more expensive to send. If you can prove that you spent some appreciable amount of computing time to send an email, it's not profitable to send 1 million emails out where no one's ever clicked on them. So how does this work? You take the contents of the header from the two, subject and a nonce, which again, we just start with 0. We're explaining a nonce right now. So you take the contents of this header, hash them up, and then anytime you hash something, the output is seemingly random. It's not actually random, it's deterministic, but it appears to be random. So there's some very small probability that you're going to see any random pattern, like say 10 zeros at the start. We can just agree that that's the pattern we're looking for. You probably won't see it, but there's a small chance you would. And if you see it, great, you're done. If you don't see it, you can just increment this nonce to 1, and then try it again. and then you probably won't see it again, increment nonce, try it again, increment nonce, try it again. Do that billions, trillions of times, and eventually you will find it. You'll see a hash that has 10 zeros in front of it. So the idea here is that now you've proved that you spent a long time, not, long is a relative term, but like a fraction of a second to generate this hash, and I can then put this hash into the header of the email, send it to you, the recipient, and then it's very easy for you to verify that what I said made that hash true was actually true. You can take the nonce, because I'll put that in the header as well, and all the rest of the contents of the header that you already know. You can, concatenate them all together, hash it up yourself, and say, yep, that really is a hash with 10 zeros at the start of it. This guy really spent a half a second to send me this email, and that's a proof of work, which you've probably heard in relation to blockchains. That's, at the most fundamental level, that's how proof of work works. Merkle trees. This is arguably the most complicated subject I'm going to talk about today. So it's not strictly necessary to understand anything we're doing in the demo. So don't worry if this goes over your head. You can kind of just ignore it. But Merkle trees solve the problem of, I talked about earlier, if we had a bunch of data in a block, a bunch of transactions, or wherever the case may be, and we wanted to store it all as one hash, because it's just easier to deal with a hash than it is to deal with a bunch of data. How can we do that in a way that lets you verify any individual piece? You can imagine you could store the hash of the entire group, and that would let you know if anything was wrong. You could take the entire group, hash up, and say, yep, this is a hash that's wrong, but you know what's wrong. You know which piece is wrong. Also, you might not have all the pieces of data. If these are transactions, and I care about whether or not you have Bitcoin you say you have, I care about a transaction that says this person paid you a Bitcoin. I don't care about the 10,000 other transactions that other people were involved in. So we want individual hashes for each chunk. That's our second attempt at solving this problem. But now there's a lot of overhead. You have to send, everyone has to have all these transactions, or all these hashes rather. It just becomes cumbersome. So Merkle roots are a pretty clever way at solving this. On the bottom here we have 16 pieces of data. A, B, C, D, E, F. They're all just our 16 pieces of data we want to store. So this could be chunks of a BitTorrent swarm, like individual chunks of the data file that we're trying to send out, or they could be the individual transactions that make up one block in our blockchain. We're just going to hash all these blocks individually. So A becomes hash A, B becomes hash B, straightforward. And now we're going to take pairs of these hashes, concatenate them together, and then hash that. So we take hash A, hash B, concatenate them right next to each other, and then just hash that, and that becomes hash AB. C and D, concatenate, and that becomes hash CD. And then move up the tree here exactly in that way. Take hash AB, CD, concatenate them, hash them, that becomes ABC. Goes all the way up to the root. This is what I called the Merkle root earlier. It's the overall, it's one hash that represents the whole tree. So how do we use this? Let's say that I have this piece of data K, and I want to send it to you, and you need to prove that I'm actually sending you the right thing. You don't know any of these other pieces of data. You don't know any of this hash. You do know the root of the Merkle tree ahead of time, but that's it. You know this ahead of time, and I'm telling you this, and you need to verify it. The idea is that I'm going to give you all the solid blue boxes, the hashes. There's one for each row, which are these like layers. I'm going to give you all these solid blue ones, and you can calculate these dotted blue boxes. You have piece K that I gave you, generate that hash. I gave you this hash L. You concatenate them together, generate that hash. This one, generate this hash. This one, concatenate, generate this hash. This one, concatenate, and you generate this hash. And you can just verify, yep, that really is what I knew the Merkle root was. So what's the key point here is that if I'm malicious and I'm trying to make a fake K that is not really the real value here, and I can give you anything I want for these four values because you don't know them, I still cannot generate a fake value here that when you get to this step, when you're merging these two and you're concatenating these two and then hashing them, you'll get the same output because of that collision resistance we talked about earlier. That's very important for cryptographic hashes. I can't generate something that will solve the problem of when you concatenate that with this thing over here, you'll get the same output here. That's the important point, and it's what makes these Merkle trees trees possible. So some kind of final points here. Blockchains aren't magic. I've said this before, but they don't verify that what is in them is actually true. We have to kind of agree as this group of people that this thing is true, and then we can record it in the blockchain. All right, so we can move on to the demo now. You will want to get your laptops out. This first link is like a chat room client thing. So you can just go here. It's tlk.io/barcamp, all lowercases. You can just go there. I will then post the second link in there, so you can just get it. It's a little bit easier. This is the chat room. When you join, if you could use your first initial and last name as your username, you don't have to like actually register or do an email or anything. You just could actually like what name you want to use. So if you wanted to use your first initial and last name, it really doesn't matter if you don't do that, as long as what you do is unique. I don't want a bunch of like Mikes and Steves in there. So yeah, I posted that link up there. Does everyone see that link, or does it go away? I can't remember if this thing has history or not. The second link to not that. This page. I'll post it again. It's stevenwetzel.github.io/blockchain.htm. I just posted it here, so you can just click on that link directly, or you can attempt to type that in yourself. So the idea here is that we're going to use that second page. We're going to generate ourselves a blockchain that we're inventing right now, basically in this room. And then we're going to use this chat room just to kind of mimic, the communication protocol that we would have if we were doing this for real. So, has everyone found their way to this page? Yeah? Okay. So this is a basic page I made to kind of demonstrate how these blockchains get generated. So if I jump back real quick to that diagram. This one, that page essentially represents the pieces that are in this header of this file. The previous hash is an input box, nonce is there. The Mocha root is just going to be data. Like I said, we don't actually have to use Mocha roots. I just wanted to explain how they use because I think they're interesting. But we're just going to put the data directly in that field. And then the timestamp, we're using username essentially instead of timestamp. All that matters is that it's going to be unique for all of us. We're not all using the exact same input. So as an example, when you start typing stuff here, it'll concatenate these four boxes together: the previous hash, the data, the user, and this nonce. It'll concatenate them right down here with semicolons in between just to help make it a little bit clearer what it's doing. And then it'll generate the SHA-256 hash down here. That's what this is. And, it happens in real time. If you type, it'll generate hashes. So if everyone types the word test, lowercases, they should see 4B7E. Does everyone see that, hopefully? Cool. So if you type the word test with a capital T, for example, this is a different string, BE74. And then what we're going to do is click this increment button a few times, and you'll notice that the nonce is incrementing, and it's changing the hash. And so we're going to do this a few times until we see a string, an output a hash, that has zeros at the start of it. 2 zeros. Oh, that one right there. So we'll see this output a hash. I can make this a little bit bigger, actually, sorry. You'll see this output a hash here has 2 zeros at the start of it. So like I was talking about hash cache with 10 zeros, because we're humans and not computers, we're going to set our goals a lot lower and only find 2 zeros at a time. But that's our goal, to find out. Hashes that have 2 zeros at the start of it. And that's going to prove that we did some amount of work. And the way we're going to do that is, again, just click this increment button, increment this nonce, generate hashes over and over again until you see the right number of zeros. And just for the sake of ease, I display how many zeros are here. It might help you. So let's go ahead and reset your nonce. Delete what's in data. I'm going to generate the Genesis block right now. Put my username in here. Genesis block is the block that does not have any previous hash. It doesn't actually have any meaningful data in here either. It's just going to be, some basic thing that we can use as the previous hash in the next block. Everyone put the same username you put in the chat room just to make it easier in this user box now. And now we'll all see different things going forward because we all have different usernames. We're going to see different hashes down here. So I'm going to do Barcamp 2018, and I am going to generate hashes until there it is. All right. So Barcamp 2018, that's Wetzel using as my username, non to 12. That generated a good hash down here. So the procedure is going to be, going forward, what we're going to do is we're going to figure out whatever data we want to encode. We're going to put it in the data field. You're going to put your own username in the user field. We're going to put this hash as the previous hash value. And then we're all going to individually click this increment button until we find a hash with the right number of zeros. And then whenever you find it, just call out that you found it. Put it in the chat room, like I'm about to do. I'm going to copy my input. I'm going to find input back here. And I'm going to put this hash back here. And now what everyone else can do is copy my input. Go back to this page, go down to the second area, verify blockchain, paste it right in here, and you'll see it just gives you the hash or whatever that is. And you can verify, yep, that really is the same hash that this person claims it is. It really starts with 2 zeros. It's the same hash they posted here. Okay. So everyone should copy this hash, 00DD. Go ahead and paste that in your previous hash, because now we're moving on to the first real block of our blockchain. You generate the Genesis block. You should have your own username. You can reset the nonce, or it doesn't matter if you do that. And let's say that my two colleagues back there, Tom and Tyler, we want to record the fact that Tom paid Tyler on Barcamp coin. So that's our payload here, our data. So everyone put that same data in. Tom paid Tyler 1 Barcamp coin, underscores in between all letters, all lowercases. Your own username. You have, for the previous hash, it should be 00DD0B. Should start with that. And now you can just begin clicking increment until you find an output hash down here that has 2 zeros. And just let me know when someone finds one. Mine Barcamp points right now.
Got one.
Nice. All right. So go ahead and copy your combined input line. Paste that in the chat. Okay. And let's see your output hash. So I'm just going to verify. Yeah, looks like it was right. Great. So you generate your first Barcamp coin block. So I'm sorry. What's your name?
Ken Graham.
Okay. So let's move on to our next block now. So let's say that Tyler paid Kent 1 Barcamp coin. That's your reward for generating that block. So reset that nonce. This is an important point. Take the hash that was posted. That's 0011F95. Paste that in the previous hash here. So we're all using the correct previous hash. And then again, the data is Tyler underscore paid underscore Kent, 1 Barcamp 1. And then your username, nonce, and you can begin mining our next coin.
Take a while.
Yeah, I tried to decide the size of the room, but
Got it.
got one? Nice.
Mhm.
All right, so go ahead and paste your combined input.
See, just before you go, could you
Sorry.
look at that verified?
I'm sorry?
Could we look at the verified file?
For the previous one?
Yeah, is that what you pasted in there?
Yeah, I pasted this in.
So that is what was generated here.
That's what that's the previous hash we all agreed upon from the Genesis hash. It's the payload from the data that we all agreed upon. It's his username, which is this hash, but that's fine, that's his username. And then it's the nonce he used, which is 15.
And that output hash should be your previous hash up above.
For this step we're doing right now, yes.
But that doesn't match.
Does it not? Sorry. I messed up my own thing. I did.
You just had originally copied the wrong one from the chat.
Oh, did I? A little confused.
Or multiple people posted at the same time.
I see.
The blockchain's been corrupted.
Yeah, that's a good point.
Wait, so which one should be that one?
So it does match that one. 001.
Yeah, that's the one you used right there. The one you
This one right
highlighted.
here?
Yeah.
Oh, and that's that one, yeah, okay. So, okay, we gave credit to the wrong person, but that's just because I'm a human as moderator.
Yeah.
It's not an actual computer, but, I guess we've moved on now with this hash, so we've recorded it as Ken having received it. So I'm sorry, did you post your output for this one?
No, do we want that 0011 in there? In the
Yes.
previous? Okay, then,
The entire combined out,
Yeah.
input, this entire line.
mhm. Make mine.
And what's your name here? This chat room?
T Marin?
Alright, so yeah, that's our next. See here, yep, the vertical is 00AB515. That's the, wait. Oh, I'm sorry, can you go to the hash now that you've got to, that you're claiming?
Yeah, that,
Yep, so it's the same hash I just found. So this is a properly verified one. My apologies for the previous step, but I'm gonna, oh, no, not that. I'm gonna take this input hash, is input payload, paste it here, see that it produces 00AB515, then we take that hash, put it as a previous hash, and now we're ready to generate the next block in the chain. And we don't have to go through this process again, but I think the point here is that it should be clear now, if I want to go back and change something in that first block, it would be very difficult because I'd have to spend a lot of time clicking through and finding a new nonce that would generate the right number, the right output hash or the right number of zeros. And in that time, the rest of us are moving on with our lives, generating the next block, the next block for that, the next block for that. So that's why you hear about things like 51% attack, because if this left half of the room, which has 2 more people on it, all decided, hey, we're going to work together to corrupt this chain, you could all work together and make your own version of the chain, because you'd be just faster than the rest of them. But the further back in the chain you want to corrupt, the more and more of a head start the right half of the room would have, my right. And so you have more and more work to do to catch up to that point, and which is more difficult.
If we were looking for 10 zeros, would that actually take a really long time for a computer?
I honestly, each zero is 16, so 16 to the power of how many zeros you're trying to find is how many possibilities there are, and then it's, yes, I think it's the answer. If you do this number, then divide it by 2 for the average, so is that 3 to 4 here? So this is about how many hashes would have to be generated, so that's what, 1,000 million, about half a trillion hashes, which honestly wouldn't take that long, I think, for most computers doing shop to do 6. Long is a relative term, I guess, but it might take minutes or something, I'm not sure. Most computers are very fast at these hashes these days. So, that is all I have. I have further reading here if you want to take a picture of this or talk to me afterwards. I'll share this slide with you so you can get to the links. But that's all I have, unless there's questions. Yeah.
So how does Bitcoin's, I think his name is Satori, how did he make it progressively harder? Because that's the whole point, is they become more scarce as you go. And
So-
I'm curious how that works.
You just increase the number of zeros you can generate.
That's what I was
That's-
saying.
that's-
So
that's-
each deputy bumps
Yeah.
that, so now you gotta get 11 zeros or 12
Right.
zeros.
And that's your parameter you can tweak to make it harder or more easy, but everyone has to agree to this number of zeros.
Yeah.
And that's, that leads to a whole bunch of different ways you can have everyone agree on this, but yeah, that's the basic idea.
Why are we not all using Hashcash to stop spam?
I don't know. That's part of Hashcash, I won't talk about Hashcash too much more, but that's part of Hashcash is that every email product can use it independently. So Gmail can decide, hey, this Hashcash thing is great, we're gonna start putting these Hashcash hashes in our headers, and then Hotmail can just ignore it. They don't know about it, they can ignore it, but then Yahoo can use it. They can say, yep, that works. So in my spam filter, I'm gonna put the ones that have Hashcash a little bit higher, it's a little bit less likely to be spam. It's a great idea, I don't know why. We can maybe start an email provider. Any other questions?
Can you talk a little bit about how the decision process of adding another zero to it becomes more rare?
Honestly, not really, because it's so different for every different system. Bitcoin and Ethereum and then all the other millions, thousands of them have different consensus systems, and it's kind of something they have to think about from the start, and that's why Bitcoin, has the curse of being first, so they didn't have all the forethought, but at the same time they have the early start advantage, so they have those numbers. But yeah, if you just look at all the different systems, they all have their different ways of generating these consensus, and I'm not an expert in any systems in particular, which is why I don't feel super comfortable giving you too many examples, but yeah, so I mean, that's about it. Yeah.
Disclosure, I'm not a programmer or coder, so this is way over my head. But as far as the utility of blockchain, so I'm in the healthcare space. I know the financial industry, that's sort of where blockchain kind of came out of. I'm sort of trying to understand sort of the utility of blockchain, sort of the private companies that are using it internally for their own data protection, and then there's companies, probably a lot of people in this room may think of ways to monetize it. This is a technology that can be widely useful. And then there's sort of the public domain, where you have municipalities that may be sort of having sort of more open sort of source blockchain for data. In the healthcare space, there's a movement towards giving the medical record back to patients, and as well as some credentialing things. And it's interesting to me, but at the end of the day, who develops the blockchain and who sort of has access to it and owns the data, the proverbial data. And so I'm curious, just as somebody that's kind of on the front lines, sort of what is your philosophy as far as how this will be used 5 years from now, 10 years from now?
Well, I think that when you're talking about blockchain and uses in the future, the most important point that I kind of tried to reiterate on is just that it doesn't prove anything's true. It doesn't really provide security beyond just saying what we agreed upon was true a year ago is still here in this record. It hasn't changed in that last year. So for your example, I'm sure there are uses, but I'm kind of can't think of any off the top of my head.
I throw it out there,
Yeah.
23andMe.
Right.
Use my DNA scan as the source for generating a root, if you will. And now you can always validate that you're looking at my DNA, which become very important if you're going to prescribe a treatment or drugs. because they need to match up.
Right.
More and more, we're looking at the
You
DNA
need permission for
implications.
that, yeah.
And permission, exactly.
And it's trackable.
Yeah, because
Yeah.
often, what's the most common problem in hospitals? People getting prescribed the wrong medicine. And
Yeah.
DNA is so important for that, so that's the way to do that validation.
Another-
It's just throwing out an idea,
Yeah.
not.
Another idea you
speaking for-
gave me while you were saying that was just the kind of, I guess, a log of prescriptions would be the other use case. Just like this person was prescribed this amount in this date, and that would just be useful for, any transactional type thing, I guess, would be stored in there.
Right.
So I don't know, I'm sorry, did I really answer your question? or-
Yeah, no, I mean, somewhat, yeah. I think there's a country, I don't know if it's Croatia or Estonia or one of these sort of former Soviet bloc countries that is actually sort of, I think, really putting blockchain, they're like sort of the Wild West, kind of implementing in their public infrastructure as far as like identification and, a bunch of other stuff. It's
Mhm.
kind of interesting, so, to see sort of the directions that this is going.
Yeah, for sure. Anything else?
Is there a concept such as master key and who owns it, if at all there is any?
I mean, not really. I mean, so the idea is that we all kind of just agree upon a certain set of parameters is the way this works. And if everyone just agrees, no, this is the key, and you're saying this is the key over here, everyone's just gonna ignore you, If you don't have at least 51% of the nodes in the system, so you can overwhelm everyone else.
Is there any, speaking of that 51%, I wonder if anybody's working on a mechanism to prevent that, to defeat that hack. I know there was just one publicly that came out, I forget, maybe about a month ago or so.
Yeah, there are a lot of
Somebody took
very
over a lesser
specific-
cryptocurrency
Yeah,
and managed to get 51% so they could take control.
right.
I was curious if anybody's working on mechanisms to do.
There are. It's a fundamentally difficult problem unless you're going to promote people to have a higher level of authority in the system. If everyone has the same level of authority, and if more than half of you say something's true, you
Yeah.
kind of have to trust that.